Mechanics 1, Chapter 10, Section 10.3, Forces and Acceleration. In this video, we will go through the forces and acceleration, or Newton's second law. So what is Newton's second law, first of all? Newton's second law of motion states that the force needed to accelerate a particle is equal to the product of the mass of the particle and the acceleration of product. F equals to m times by a. Okay, where F is the resultant forces and its unit is Newton. M is mass in kg and a is acceleration, meter per second to the minus 2. Okay, first example. So before first example, we've got another formula, which is the formula for gravity. Okay, weight is equals to mass times by gravity. Okay, so gravity is the acceleration due to the gravitational force of the Earth. Okay, so which is normally 9.8 meter per second squared. Okay, so example 5 from the textbook. It says find the acceleration when a particle of mass of particle is 1.5 kg is acted on by a resultant force of 6 Newton. So we just directly use the Newton's second law's formula. F equals to ma. So F is 6, m is 1.5 times by a. A is 6 divided by 1.5, which is 4 meters per second squared, which was quite easy and straightforward question. Next example. Example 6. In each of these diagrams, the body is accelerating as shown. Find the magnitude of the unknown forces x and y. Okay, so let's draw the particle x, 2g Newton, y, and 4 newtons, and the acceleration is in this direction, 2 meters per second squared. Okay. Are in vertical direction. The forces in this direction would be x, sum of the forces, x minus 4. X minus 4 must be equal to mass times by acceleration. So this is 2g Newton. In fact, this is W. W equals to 2g Newton. It's not only mass. It's mass times gravity, which is W. Okay, so therefore the mass is m is equals to 2 kg. Okay, so 2 times by acceleration is 2 as well. Okay, x minus 4 is equals to 4. Therefore, x is equals to 8 Newton. Okay, so the next diagram is, we draw the line here. So here is the diagram for the next one. Force X is in this direction, 80 newtons, force G newton, force Y, and 20 newton downward. Okay, and 2 meter per second in this direction. 2 meter per second decimal in this direction. Okay, so we know that sum of the forces is equal to previous question we didn't work out the value for y, so we need to work out the let's work out the value for y for the previous one, and then we move on to part 2 of example 6. Okay, to work out y, the particle is not moving up or down, therefore acceleration toward up or down is equal to 0. If we write down the formula again, so r in this direction forces upward or downward is, so y, no matter which one you take positive because acceleration is equal to 0, y minus 2g is equal to mass times 2 times y. Acceleration in this direction up or down is equal to 0. Therefore y minus 2g is equal to 0, and as a result y is equal to 2g Newton. In fact, y must be equal to 2g Newton because the particle is not moving up or down. Okay, let's move on to part B of the example 6. Okay, so again, the particle is moving in this direction toward left. Okay, all the forces on x-axis, or the vertical one, okay, would be 80 minus x is equal to mass times 4 times by acceleration 2. 80 minus x is equals to 8. X is equals to 72 newtons. And the forces up or down. So, in very similar way, we know that the particle is not moving up or down. Therefore, forces upward or downward, y minus 20 newton is downward. So as we taking upward positive, downwards should be negative. Minus 4g must be equal to mass times by 4 times by 0, because acceleration is again 0 in this direction. Y minus 20 minus 4g equal to 0. And therefore y is equal to 20 plus 4g, y equals to 20 plus 4 times 9.8, which is 59.2 Newton. 59.2 Newton. Okay. So now we are done with question example 6. Let's move on to the next example. Okay. Example 7, which is quite long example. I don't write down the question, but I try to put the textbook here just to read the question together. Okay. So, a body of mass of 5 kg is pulled along a rough horizontal table by a horizontal force of magnitude of 20 Newton against a constant friction force of magnitude of 4 newtons. Given that the body is initially at rest, find the acceleration of the body. Okay. Example 7. A body of mass of 5 kg. So let's say there is a table. Okay. 5 kg is pulled along a rough horizontal table by a horizontal force of magnitude of 20 newtons. Let's say 20 newtons here. Against a constant friction force of magnitude of, so if 20 Newton is in this direction, the friction must be in opposite direction. Okay, 4 Newtons. Given that the body is initially at rest, so initially at rest means A is equal to 0, it's not moving. Okay, so let's see if there is any other forces acting on the particle. Of course, there is mg downward, 5g newtons downward, and the reaction force upward. There must be reaction force upward equal to 5g. Otherwise, the particle will move up or down. Okay, so the particle was initially at rest, but after 20 Newton forces been acted on that, so it must be moving. Let's say it's accelerating in this direction. Okay, meter per second. So we can apply the Newton's second law. F equals to ma. Okay, for the forces in this direction. So 20 minus 4, the resultant forces is equal to mass times by acceleration. 16 is equal to 5a, therefore a is equal to 16 over 5, which is 3.2 meter per second. Okay. So the next part of the question, the distance traveled by the body in the first 4 seconds. The distance traveled in first 4 seconds. Okay. So when we're talking about distance, we should know that we're going to use the what equation. So S equals to ut plus half at squared, because we want to work out the distance, and the informations which we have got is u, which is 0 because initially at rest, so u equal to 0, t equal to 4, acceleration which we already worked out 3.2. Okay, so therefore we can apply the formula. S equals to 0 times by 4 add half times by 3.2 times by 4 squared. Okay, which is 25.6 meters. Okay, the body moves a distance of 25.6 meters. So next one, part C. The magnitude of the normal reaction between the body and the table. The magnitude of normal reaction. So which I showed with letter R. This R is different with this one. This R shows the some of the forces in this direction on x-axis, and this one is the reaction force. Okay, so don't mix them up. The magnitude of the normal reaction. We know that the particle is not moving up or down. Therefore, the acceleration up or downward is equal to 0. Okay, for this direction, it would be for F equals to ma, a is equals to 0. So some of the forces would be, let's say, upward positive. So therefore, it would be r minus 5g equals to mass times by acceleration, which is 0. So r minus 5g equals to 0. Therefore, r is equals to 5g newtons. Okay, so, or you could write down r equals to 5 times 9.8, okay, which is 49 newtons. Therefore, the normal reaction has magnitude of 49 newtons. After this lesson, you should be able to do exercise 10C. I just write it down here. Exercise 10C. Okay, which is page 100 and page 164 to 166 from the edexcel textbook. Okay.